Hello, and welcome to Physics for Play. In this video, we're going to be showing how to visualize the solution to the simple harmonic oscillator differential equation that we solved last time. Let's get started. We're going to begin by animating the motion of the oscillator. So in order to animate it, the first thing I want to do is I want to make some kind of graphic. So we're going to use the command graphics. Very inventive with the naming. It makes it very convenient. And I'm going to put a few different objects in the graphic. So I'm going to put a list of objects. Lists get curly brackets. The first thing I'm going to put in there is a disk, and the disk will be my harmonic oscillator. It's just going to be a circle. And I'm going to give it a component of 0 along the x-axis, but then I'm going to make its y position be the displacement x. I'm making it go vertically up and down because we're used to springs going up and down. So don't be confused, even though we're in the second part of the list, which is the second part of the disk, which is going to be the y component. Actually, this should be a list, so let me fix that because I need to make this a pair of components. The x component here is 0, and even though this is called x of t, it's going to be the vertical component. So we've got a disk in our graphic. We're going to make that a red disk just because I like the color red. I'm also going to give this a range over which I'm plotting this. So by default, Mathematica will try to choose the range for you. It's very easy that way. But it will try to put in just the important parts of the graphic. In this case, the important part is the red disk. And when you see the red disk, if you try it without the plot range, what will happen is you'll just get a red disk and you'll be like, hey, why isn't this moving? And the reason it's not moving is that it is actually moving. You're just not seeing it move because Mathematica is moving the graphic with the disk. So it's just kind of zoomed in with the camera on top of the disk. I'm actually going to put in one more thing here just to help us visualize it. I'll put in some axes. And we'll say axes is true just to make sure they show up. Now, we're going to run this now, and you're going to see it's going to give us an error. And errors generally of graphics, you get some red square, and the graphic kind of shows up, but nothing's really there. It'll give you some error message up here. And you can guess what the error message is going to say, because I've got a blue T in my equation here. My blue T is there because the time is not defined. So it's more than happy to plug in x of t to give me the coordinate of my disk, but it doesn't know what time x of t is supposed to be taken. So there's a command in Mathematica that's going to be very useful, which we're going to use here. It's the replace all function. So what this is going to do is the replace all function replaces all of some variable with a value. So the way we're going to write that is the replace all is given by slash dot, so slash period. And I'm going to tell it what I want it to replace. And I'm going to tell it I want to replace t. And that t is going to become, so I'm going to give it a right arrow by doing a hyphen, angle bracket, which will give me a right arrow. And I'm going to start with t equals 0. So I'll replace that t with a times 0. And you're still giving me an issue. Why are you giving me an issue here? What did I do wrong? Something's cranky. Oh, I think maybe I need to put... Are you complaining that it's not in the list? No. All right, we've got some kind of issue. Oh, that's the issue. Yep, never mind. I am an idiot is the issue. Haha. Idiots unite. If I look at x of t, you see what's wrong. We have not defined any of the constants in the x of t, so I still need to do that. I'm going to go ahead. I'm actually going to use the original form just because I like it better. I like the sine function. I don't like the sine plus the cosine. Cosine's okay, sine's okay, sine plus cosine, just, it's too much trig. We want to define this, but we also want to define what our amplitude is. So I'll say the amplitude is 1. I'll say the angular frequency, I'll make that 2, mix it up a little bit. And I will say the phase shift, we'll start off with a phase shift of 0. So this should give us just a sine function that starts at 0. So if I run this now, hopefully you're happy. Yay, sweet. Now, if I change my time, this will move forward in time. And since it's a sine function, I'm going to just move this up just a little bit. I'll make, instead of t equals 0, I'll make it 0.1. You can see it moved up just a little bit. Let me increase it a little more. Moves up a little bit more. If I increase it a whole bunch, you can see it starts to go the other way because it's going up and down. So rather than having to plug in times at every step here, which is going to be a whole bunch of work, it'd be much more fun if I could just animate this whole thing. So I am going to wrap this graphic in an animate function, and I am going to animate it from t goes from 0 to, we'll have it go through a full period. So we'll have it go from t equals 0 to 2 pi. And we'll see that. And I'll just take a moment because it's, the animation is thinking while my screen is a little bit frozen. There we go. You can see it going up and down. Let's change a few things on here because it's now that I've got my animation up and running, I can make this a little more interesting. So let's increase the amplitude. So you could see before, let me do this before I actually run it. You can see it's not oscillating very much, and that's because the amplitude is only 1 on a scale going all the way from -10 to 10. So that circle is bouncing between 1 and -1. Let's make it bounce a little bit more by running this code, which will reset the amplitude to 10. And now you can see it's bouncing a lot more. We can change the frequency. So if I want to slow it way down, I'm going to change this to a frequency of 0.1. And I'm going to increase the time on this because, well, let me keep the time the same. It won't go through a full cycle, but you can see it's going much slower now because I've decreased the frequency at which it moves. And if I increase the frequency, so now that might be too fast. Let me increase it to 5. You can see it's going back and forth really fast now. Change this to 1. Now if I run this, you can see that's a decent frequency. Let's look where we start. So we start at x equals 0, or excuse me, at x equals 0 at time 0. And that's because we're using a sine function that's not phase shifted at all. Sine of 0 is 0, so this is going to start at x equals 0. You can change this to pi over 2, which will phase shift it by pi over 2 radians, which means I'm going to start now at the top. So now at t equals 0, we're not at 0. We're at the maximum amplitude, which is at 7. Note, you can also do this in degrees if you want, but you do actually have to spell out degrees or degree, and it works just the same. By default, Mathematica will assume you are doing, you're putting your units in radians, not in degrees. So you want to make sure you are paying attention to that. Don't throw in 90 without degrees, otherwise you'll get a wrong answer here. So once you can animate it, you can kind of play around. You can see how the changing different parameters changes different settings on the animation and how it really changes the physics. But you're not just restricted to animations. You can also plot it as well. So I'm going to go ahead and we're just going to do another plot here. So we'll do plot. I am actually going to copy this, and the reason why will become clear in a moment. I'm actually just going to copy the functional form. So Control C that, paste it in here, and we're going to plot that from t goes from 0 to 10. And we are, again, let's give it an axes label, and we'll put the labels in a list. It'll be time on the x-axis, so it'll be time t in seconds, and along the y-axis, we will put the displacement. That's the displacement x, which we'll say is in meters. I'll give a capital letter here just to be consistent. We'll give it a plot range of, we'll go from -10 to 10. We will do, what else do we want to do? Let's just start with that for now. See what that looks like. And you can see our values here. As before, we can change the values. So if I make the amplitude 3, you can see that gets smaller. If I make the amplitude -3, you can see it flips. But I'd like to be able to do that. I'd like to be able to change the amplitude kind of quickly rather than having to reevaluate the code every time. It'd be great if I had some kind of scroll bar or some sort of dashboard where I could do that. It turns out Mathematica is great. It'll let you do that. If you want to manipulate a function, you just use the command manipulate. So we're going to wrap this whole plot in a manipulate function, and we're going to manipulate a few different variables. So I'll start simply. I'm just going to start with an amplitude, and let's make our amplitude go from -10 to 10. So these are the values of the amplitude that I can choose. And I forgot the square bracket, so let me put that there. Now, by default, it's going to start with the first number I give it, but I can change the amplitude, and you can see I can go back and forth. And I can see whatever value I put in. I can just change it to be, I can change it in here directly if I would like to. Again, sometimes it's helpful if you want to make these things look nice. So for example, if I want to put in a particular value, let's say I want to start it at 1, I can do that. I can just do this. The amplitude starts at 1. If I would like a label that's not just A on here, I can do that as well. So I'm going to just say, in case anyone has forgotten, that this is the amplitude A, and you can see that showing up in here. You can also put in styles and other stuff as well. Let's see what else we can manipulate, because we've got a few different variables in here. I'm going to just copy this, but instead of amplitude, let's put in the angular frequency, which will start with 1. I'm going to change the label on that to angular frequency, symbol omega, and let's let the angular frequency go from 0 to 10. And let's also put the phase shift in there. By the way, as I'm adding these, you can see there, the manipulated variables will turn green. So watch this phi naught. It's black now because it's defined. As soon as I change this to phi naught, this omega to phi naught, you can see it turns green because now it's inheriting the phase shift is inheriting the phase shift from the phi naught from the manipulate is taking precedence over the predefined definition. So it'll be locally defined, and it's going to use that local definition that is defined by the manipulate function. So let's just write our phase shift this way. And we'll let the phase shift go from 0 to 2 pi. So again, we can increase our amplitude. We can change the frequency. So at high frequency, it goes up and down and up and down and up and down really fast. At low frequency, it goes up and down really slow. Phase shift, for any positive phase shift, that actually moves the it takes the whole graph, grabs it, and drags it in the negative direction if the phase shift is positive. So it's opposite what you might think. And it drags it in the positive direction if you have a negative phase shift. So if I move the phase shift in the negative direction, it'll move the plot to the right. And this is the thing that's great about being able to do this computationally, is that you can manipulate these variables and see what they actually do really fast. So it allows you to play. Quite a bit. You can even animate through what these variables look like. So there's a lot here that you can do to really learn and get a sense for how the physics works. That being said, since we are talking about harmonic oscillators, and since I mentioned it earlier, it's helpful to do one more plot. I won't go through the manipulate on this, but I'll do one more parametric plot. I'll do one more plot to get the phase shifts, or get the phase plot rather. In this case, I'm going to do what's known as a parametric plot. Before I did a contour plot, and the reason why it's not a contour plot here is since we have x of t as a function, it is parameterized with respect to t. I also have the velocity, which is we can write as x prime of t. The prime is the first derivative, just like the double prime was the second derivative. So we can do our phase plot. We're going to take this from t equals 0 to 10. Now you'll notice that before, when we did the plot, let me minimize some of these to save myself some space. When I did the phase plot up here, I used a contour plot. Here I just wrote down the full equation. None of it was parameterized. I just wrote it as functions of x and velocity. A parametric plot gives you a plot where you're tracing x of t and x prime of t. You're tracing these functions throughout x and y space as t goes from 0 to 10. So to show you what that looks like, here we go. Looks like this. If I make this a much smaller number, if I make this let me make it a little bit bigger. Make that go, x goes 0 to 0.7. You can see it's starting to trace out that arc throughout space. It's kind of looping its way around the circle. So as t is getting bigger, it loops more and more of this circle. At 2 pi, it maps the whole circle. If it's a little bit less than 2 pi, you can see it doesn't quite map the whole circle. So this is another way to do a phase plot. Again, just because I'm a stickler for such things. Let's put a plot label in and give it a list where the x value is the x coordinate. That's the displacement from equilibrium. And the y coordinate is in this case, it's that x prime, which is the velocity. And it helps if I spell velocity right. Come on, that's in meters per second. Oh, sorry, I don't want plot label. I want axes label. Plot label just gives you a title on the top. Axes labels the actual axes. So yeah, we get another phase plot like we have up top there. But the important thing is you can solve this differential equation, and then you can plug it in. You can make plots, you can make animations, you can do a whole bunch of neat stuff once you've solved that differential equation. We're going to stop here since this video is getting a bit long. Join us next time where we'll talk about things like the difference between the period and the frequency and the angular frequency, cover some general aspects of simple harmonic oscillators you may have heard in class. Like the video if you liked it, and if you'd like to see more, please click subscribe.